recording. We're recording. Yeah, so here's what I have on my to-do list for today. We're going to discuss the quiz, which is tomorrow. And coming in? No. Then we'll go over some stuff from yesterday. Yesterday, we did all these examples of like limits of compositions, so we can go over some of those. And then there's this one topic we missed from a while back. This thing called the squeeze theorem. I think it's totally fine that we didn't go over it. It was actually in 2.3. I think it was fine that we didn't go over it, but I do think we should touch on it a little bit because we are going to use it in chapter 3. So, you know, not right away in chapter 3. It'll be a few sections before we use it, but I think it's still worth kind of spending some time on it so we don't have to spend as much time on it later. And then we can just, of course, do sort of a Q&A review if we want to. So let's begin. Quiz tomorrow. Guess I'll put a little bit of information in here. Quiz is tomorrow in class. Okay. You're going to have 30 minutes to do that quiz. You're allowed, I mean, really, you're going to need a calculator. That's about it. Bring a calculator.
I remember you said one time that you were going to bring like laptops so we could use Desmos instead.
Yeah.
Is that still happening, or
I
need to
am
bring our...
just now realizing that I forgot to request those. I think if I do it now, I can probably still get them for tomorrow morning. But try to bring a calculator just in case. If you don't have a calculator, don't go buy one. I have some calculators that I can lend out, and also you're really only going to need it for like one of the problems, and so we can share, or like you can come up and use the computer at the front of the room. You really only need it when you're doing the solving a limit numerically, where you're just filling out a table, you know, like you definitely need one for that. But for most of the other problems, like the graphical one, like solving a limit graphically, you're just looking at a picture. You don't need a graphing calculator for that. And for the analytical solutions to limits, you really, I mean, mostly algebra. So you might just use your graphing calculator or Desmos to sort of check the answer. So.
Do you know how many questions are going to be on the test?
Like 5, I think.
Okay, thanks.
It's not going to be very long. I'm calling it a quiz, not a test, because I really am not thinking of it as a test. A test is more cumulative. A quiz is more like just a few things, you know?
So no tangent lines and stuff?
That's a good question. Yeah, we're not going to do tangent lines right now. The tangent line stuff we're going to get back to right at the beginning of chapter 3. So I don't think there's any point doing it on this quiz. We're going to do it right away, like Thursday anyway. It's 3.1. So no tangent lines. This quiz is just going to be about limits only. Okay, so regarding limits, you know, you've got sort of like three approaches, right? So numerical, graphical, and analytical, which involves like algebra, etc. You know. And one of the things you might need to use is this U substitution idea. So I'll put that for compositions. That would be something you might need to use. That falls under like an analytical solution. Yeah. Any other questions about this quiz coming up?
I got a question on like the difference between the numerical idea and like solving it numerically versus solving it algebraically.
Do you want me to just explain the difference between those?
Yes.
So solving a limit numerically is where you are like building a table of values and you're plugging in numbers that are getting closer and closer to whatever X is approaching. So if X are approaching like 5, you do like 4.9, 4.99, 4.999. And you are like actually just plugging those numbers into the function, right, to evaluate the output. And you're paying attention to the Y values, and you're making a table and you're looking at what the Y values are approaching in order to guess what the limit is. And you should do it from both sides. So 4.999 and also like 5.001, that sort of thing. So that's evaluating a limit numerically. It's not really as rigorous of an approach because it does rely on making a guess, Whereas solving or evaluating or solving, I guess solving is not really the word we use. It's evaluating a limit analytically. That's more like you are you're using algebra to simplify it until it is you remember how, if you can like factor and cancel, then you can get it so that it is defined at the X value that you're approaching instead of having like a 0 over 0. Then you can use direct substitution to evaluate the limit. So
wait, is the quiz today or tomorrow?
Tomorrow. Yeah, tomorrow.
Oh. So is it like so it's in class, right?
Yeah. Just come to class.
How do I study for it? Do I have to
do the homework? Look over the comments that I've provided on your exercise sets. That's how you should study for it. Look over your notes.
Okay.
Yeah. Look over the examples we've
Wait,
done.
is exercise 1 going to be a part of it, or is like it's only exercise set 2?
It's going to cover some topics from exercise set. Well, no, nothing from exercise set 1, because exercise set 1 was entirely review, and exercise set 2 it's going to be more similar to exercise set 2. Yeah, but it's also going to have this U substitution thing we've been doing lately, which exercise set 2 did not have. So it's a little more. That makes sense.
Okay.
I want to circle back to Hannah. Did my explanation of the two make sense?
Yeah, that really helped. Thank you.
Excellent. I think that the thing that really characterizes an analytical solution is that it is based on the theorems. And the word theorem means like a fact from mathematics, like something that's true that you can prove. And so things like, there was this theorem I told you guys about that said that if two expressions are equivalent to each other, except possibly at one particular value where one of them might be defined and the other one's not, right? Remember how you can factor and cancel, and then it's like equivalent except for it was undefined and now it's defined. The theorem is that those two expressions will have the same limit at that X value where they differ. And that's because they're the same everywhere else. So, I mean, but yeah, what characterizes an analytical solution is really that it doesn't involve any guesswork. It's just it's based on the theorems. Now, there's a question in the chat from WaveLol. Who are you, WaveLol? Just curious. You don't have to. Who's WaveLol? Well, whoever you are, welcome. I assume you're in this class. Somebody I know. Good question. Do we need to start at 4.9, or can you start like later on? So you can start wherever. You can start your like sort of exploration of the limit at whatever point. So you could start at 4.999. But then you don't want to just look at one number on each side. So don't just look at 4.999 and 5.001. And the reason for that is you need to be able to see some trend towards a value, a fixed value. Maybe I can show you an example of why you need to do that.
I have a question.
Can you hold it for a second?
Yeah.
I just want to finish answering this question from Elijah. Thanks, Elijah. Here is an example of an interesting function. Okay. Sine of 1 over x. If you are looking for the limit of this function as x approaches 0, if you just do f of like 0.001, that is not the correct limit. This would be the wrong answer. Okay. And the reason that's the wrong answer is because look what happens when you do
The Holocaust memorial. Reason.
Look what happens when you do a couple of other numbers. Yeah, this was 0.001. Here we have 0.0001 and 0.00001. And you get, totally different things, right? Totally different things. So there is no trend here. There's no pattern in what this is approaching. This is just randomly jumping around. And the reason it's randomly jumping around is because it's doing this behavior called oscillating. So in fact, the limit does not exist. But the point is, you wouldn't know that if you only looked at one value. So this is why you need to look at several values to observe a trend. If you just look at one number and assume that's it, you could have accidentally, you could be in this situation, right? Where actually the limit doesn't exist and you just totally failed to recognize that because you didn't examine it enough. Does that make sense?
So there's no way to know that the limit doesn't exist until you actually like graph it out with, the values and everything for this one.
Well, the graph isn't strictly necessary. The point, I think the bigger point is looking at a sequence of numbers getting closer. If I maybe do another one or two here, 1, 2, 3, 4, 5, 6 zeros, right? It becomes pretty clear.
No pattern kind of thing, no trend.
Yeah, that there's just no trend. That's right. Now, I say it becomes pretty clear because, that's kind of the best you can do. Remember that with a numerical approach like this, where you're like making a table of values, plugging in numbers to explore, you're never going to prove what the limit is with confidence. You can't. Like this strategy cannot prove the limit. Only an analytical solution can do that, right? So yeah, I mean, the best we're ever going to get is an educated guess out of this strategy. And I guess our educated guess based on this information would be that the limit doesn't exist. And that does happen to be true, but we actually don't even have the tools to prove that just yet. So don't worry about it. Great question. So Adam, you had a question that I asked you to hold off on for a minute. Go ahead.
Are we supposed to do chapter 3 homework?
Chapter 3, we haven't started chapter 3 yet. We're going to start chapter 3 on Thursday.
Oh,
Did you mean the chapter 2 homework? The chapter 2 homework, yeah, the chapter 2 homework, you should submit a preliminary grade by tonight. Tonight is the deadline to submit your initial grade to the grade book. Remember that you can do more homework later. If you didn't do all of the chapter 2 homework, you can do more of it later, and update your grade. So that those homework quizzes in D2L, you can do them any number of times. There's no limit. And if you don't get it done by tonight, all that's actually going to happen is I'm going to pester you about it. I'll just email you and say, hey, please submit a homework grade. I want that in the grade book. All right, just so I can see your progress and see where you're at. Okay. So it's not going to affect your grade if you don't do it by tonight, but it is a deadline in the sense that I want to see it. Okay, I want to see where you're at. So anyway, yep, thanks for the reminder. Please do that. Chapter 2 homework. Let's, if you guys are ready, let's go ahead and move on to our second thing. I think we've discussed the quiz. Why don't we go over some limits of compositions from yesterday? Sound good? Let's look at an example. Let's look at the limit of the natural log of 1 over x squared as x approaches infinity. Okay, let's begin with the limit of 1 over x squared. Okay, do we know what this is?
0.
It is 0. Good. 1 over x squared is, its limit is always going to be 0. Sorry, anything of the form a constant divided by a power, a rational power of x, positive power. As x approaches infinity or negative infinity is always 0. This was our theorem that we had. Theorem. Yeah, it's just an example of that, right? There's one. There's our starting point. Now we can say, let's let u equal 1 over x squared. Now we can say as x approaches infinity, u is approaching 0. So this is going to be the limit. I can rewrite this original limit as the limit as u approaches 0 of the natural log of u. Okay. Now I've simplified the limit. It's no longer a composition, right? This is the u substitution approach, right? We're replacing our 1 over x squared with a u. Let's do a little highlighting here. If u equals 1 over x squared, then this is a u, and also we're changing the limit so that it's about the variable u instead of being about x. Here's a mnemonic. You want, when doing a change of variable or a u substitution of some kind, you want to forget your x and make it all about u. Okay? Change of variable, life lessons. It's a mnemonic. It's kind of silly. Forget your X, make it all about you. All right, so that means that not only do you want this inside here to be all about you, but you also want this to be about you, right? There should be no more X's involved when you do this change of variable. So now we can evaluate this limit, right? And this is one of those that you should have memorized, right? And like I've been saying, the way I tend to memorize these things is just to think about the graph. So now there's a detail here that we were kind of missing, because normally when you say the limit as something approaches 0, that means from the left and from the right. So we'd have to consider X approaching 0 from both sides like this. Well, from one side, from the right side, we're going down towards negative infinity, right? But from the left side, the function doesn't even exist. Negative numbers are not valid inputs for the natural logarithm, at least not unless we want to talk about complex values, which we don't. At least I don't. Not right now. That's not in this semester. That's another class. So what we're missing here is this. Down here, when we were evaluating the limit of 1 over x squared, 1 over x squared looks sort of like this. Okay. 1 over x squared looks like that. Again, this is a graph. You should just know. One of the purposes of pre-calc is to familiarize you with all of these like common basic functions. So I would hope that you guys have like studied those. If you haven't, you should graph them all. Graph all these basic functions, just like familiarize yourself with them so you can draw them. Practice drawing them. I could walk you guys through that if you wanted. Let me know if you're interested in reviewing basic functions and their graphs. Okay. But the point I wanted to make here is that while this graph is approaching 0, it is doing so only from the positive side. Because when you put a large positive numbers getting close to infinity into this x here, the whole result, 1 over this large positive number, is going to be positive. So this is really only approaching from the right-hand side. So I could be more specific about this limit and say this is u approaching 0 from the right. And then I don't need to worry about what's going on over here. I only need to worry about from the right side. And so this is very clearly negative infinity without any ambiguity about whether it's a one-sided or a two-sided limit. It's actually a one-sided limit. Okay, but that you'd have to recognize the fact that these outputs are all positive to recognize that this is only approaching from one side, not the other side. So that's important. That's kind of, a little bit tricky to recognize. It's kind of up to you to realize that this is a one-sided limit. It's not something that's just going to be handed to you. So that's one place where these composition problems can get a little tricky. Okay, they're not all like that though. Some of them are more straightforward. You do another one? Yeah. I don't like the new thumbs up. I don't like it being animated. That kind of bothers me. I don't know. Can you guys see that the thumbs up and the thumbs up is animated now?
No.
Oh, okay. Yeah. Maybe it depends on how recently you downloaded Zoom. But I have an updated Zoom and I don't like it.
I just use the web version.
Web version? Yeah.
Yeah, just click the link from D2L and
That's the way to go. Let's see. Real quick, there's a question in the chat. Yeah. So the question is why was it at first x approaching infinity and then it became u approaching 0? Why was that? Okay, so the reason it was x approaching infinity is because that's just the problem that I wrote, right? That's just the problem I decided to look at here. So that came from me, right? I decided that. But then this did not come out of nowhere. This came from here. Okay. You determine, so setting, so, and it also comes from here, right? This definition. So if you decide u equals 1 over x squared, you figure out the limit of 1 over x squared as x approaches infinity. That tells you what u should be approaching, right? It's not just a random, it doesn't just come out of nowhere. It's determined by this limit that you solve.
I have a question. So when you determine that ln, like, to the function of u equals negative infinity, but then you said the theorem equals 0.
Oh, these aren't related to each other. This one and this one,
Oh, okay.
those are unrelated. This one, this theorem told us that limit
Oh, okay.
because constant divided by x to a power 1, like, you know, constant divided by x to a power 1 divided by x to a power. The power here is just called r. It could be any rational number, but here it's 2, right? So the point is that this is this type of function, and the limit tells me, and so the theorem tells me that whenever you do a limit of that at either positive or negative infinity, the result is 0. So that's where that came from. This is otherwise unrelated. This is based on, you know, just the picture, I guess, like just knowing. This is just information about the logarithm that you guys can figure out just by knowing the behavior of the logarithm. We know that a logarithm, you know, we know that any logarithm has a vertical asymptote at 0.
I have a question.
Just part of it.
Yeah, but it's going both sides. It's going infinity. Wait. So it's going positive infinity and negative infinity. Is that true? Or is it not going to positive infinity or negative infinity?
The logarithm?
Yeah, the graph.
Let's look at a logarithm on Desmos. Might be better to look at it somewhere where it's going to be nice and precise. Open a new page. Oops. If we graph ln of x, it looks like this. Down here, it's approaching negative infinity. You can see it becomes nearly a vertical line. It doesn't actually become a vertical line, but it gets very close to vertical. Yeah. So that's the behavior that we were seeing as the x values are approaching. Here, let's put a point on here. Whoops. Right, as my, oh, and then let's put like a 0. There we go. Okay, so I can drag my point along the x-axis, and you can see the point on the graph, right? And as I drag it close to 0, what's happening to that point on the graph?
It's going down.
It's shooting down. That's right. You know, and so that's why the limit is negative infinity.
Oh, wait, so what if it's shooting up? Then it's positive infinity, right?
Yeah.
So if it shoots from left to right, it's not still positive infinity?
I'm not sure I understand what you mean.
What if it shoots from left to right? You know, like,
That wouldn't really happen because you're controlling the left to right by like kind of thinking about where x is going. Left to right is determined by the x value, and that x value, you're controlling it. You're saying x is approaching 0. So the y value is the only thing that can kind of shoot off to infinity. Unless you're taking unless you're talking about, if you're talking about the limit as x approaches infinity, that would be what's going on over here. And then you got to ask what's happening to this y coordinate as x goes way off towards towards infinity. Is that kind of what you're asking?
Oh, yeah, okay.
Maybe. This graph, it's hard to tell, but this graph does go towards infinity as x goes to infinity. This is always increasing, and it increases without boundary. Like it never, there's no horizontal asymptote on this natural logarithm graph. Logarithm graphs never have horizontal asymptotes. It's kind of hard to tell that because it doesn't look like it goes to infinity, but it actually does. It just does it very slowly. Yeah.
So can we use the graphing calculators to like graph the lines?
Yes. Yeah, you can always use graphing calculator to do whatever, you can graph your functions and look at pictures. Yep. I'll always be allowed. Okay. Let's pick another example from yesterday. Let's do e to the power 1 over x and take the limit as x approaches 0. Okay, so we start by looking at the limit as x approaches 0 of 1 over x, which is the inner function, right? Because this is a composition. We've got e to a power, and we've got the 1 over x on the inside, right, in that power. So we look at that inner function. Its limit is what? You guys remember? As x approaches 0, here's the graph of 1 over x. It's this hyperbola. Let me see if I can graph it nicely. It looks like that and like that.
Wouldn't that be both
Undefined?
positive and negative infinity, so it would be undefined?
Correct. Yeah, we'll answer does not exist. That's correct. Yes, it's going towards positive infinity from one side. That's as we come in from, from the right here. But if you come in from the left, then we're talking about approaching negative infinity. So these are not the same, therefore does not exist. Now, if you encounter this situation where you're working with a composition of functions and you start from the inner function and the limit doesn't exist right away, the overall limit of the composition also does not exist. Okay. If the inner one's limit doesn't exist, the overall composition's limit doesn't exist either. It's like you were working through the chain, like you were trying to work through the chain and you got stopped. That's it. It's over. So let's look at another one, slightly different. If I look at a one-sided limit this time of the same exact function, now I only need to consider the limit from the right-hand side. So when I do this, limit as x approaches 0, I only go from the right. And if I examine 1 over x only from the right side, it's positive infinity. So this time, I don't just stop. This time, we say, well, let's see what happens at positive infinity. Right? This time we can say, okay, if u equals 1 over x, we have u approaching positive infinity. So I can carry on with this limit as u approaches positive infinity of e to the u. And what does that equal to? Limit.
Infinity.
There we go. Infinity. Okay. Yes. Let's draw the graph of e to the x. All right. Whew. Looks like that. Now let me draw it slightly less in the way of other things. Right. Over here, as x goes out this way, we've got points on the graph that are going up, up, up towards positive infinity here. So yes, this is just infinity on that one. Now, contrast that with if we had been approaching 0 from the left of this function, e to the 1 over x. I'm sticking with the exact same function. These 3 examples here are all with the exact same function. Okay, so just so you know. So now, now if I'm approaching 0 from the left, things work out a little differently. When I look at 1 over x, this time I've got this side. So now it's negative infinity. So now I have u approaching negative infinity when u equals 1 over x. And so e to the power u, as u approaches negative infinity, on this graph of e to the x down here, I want to look on the other side. I want to look over here. What's the limit on the left side?
0.
Yeah. That limit is equal to 0. Sorry, I didn't label my graphs. Up there, I was drawing the graph of 1 over x, and down in the bottom there, I was drawing the graph of e to the x. Does that answer your question, Hannah? So
Yeah, I thought you said that they're all the same. So,
oh, they
yeah.
are all the same function, but but the graph I'm drawing is not the graph of the function that we're looking at here. Let's see what the actual graph of the function is.
Okay.
The actual function is e to the power 1 over x, which looks like this. And that's a little different from anything that I was drawing, right? Because I wasn't actually drawing the graph of this. I was drawing the graph of 1 over x, and then I was drawing the graph of e to the x, like just the individual components that are being composed together here. Does that make sense?
Yeah. Sorry, I must have missed that.
That's okay. Yeah. I do think it's interesting because we never really needed to look at the graph of the whole composition. We just look at the graph of each piece individually and, use those to help us follow through the limit. Yeah. There's a question, will there be something like this on the quiz tomorrow? Yeah, something like this, some sort of composition like this. Probably involving like an exponential or a log function, because those are common. Folks, we're going to be doing a lot with exponential and logarithmic functions this semester. We're also going to be doing quite a lot with trigonometric functions, but not quite yet. The trig functions, we haven't gotten to that yet. But yeah, all those functions you learned about, polynomial, rational, exponential, logarithmic, sine, cosine, tangent, everything comes into play in calculus. I'm gonna do it all. And we're gonna mix them together too. Just throw them all in a pot and mix them around, and it's great. Delicious. Okay. I'm being sort of slow today, so we're not going to get to squeeze theorem. We'll get back to that some other time. Don't worry, squeeze theorem. We'll get to you eventually. We don't really need the squeeze theorem until we get to the trying to figure out the derivative of like the trig functions like sine and cosine. So I think maybe I'll just wait until we get to that point and then teach you about the squeeze theorem like right when we need to use it. Does that sound good?
So if we have a question in the textbook about squeeze theorem, what would we do?
Skip it for now.
Okay.
Yeah. You can go back and work on that in a couple of weeks. Maybe next week. I can't remember what section it is that we get to the sine derivative, but I think it's like 3.4, I want to say, just right at the end of next week. Anyway, yeah, skip it for now. Let's do another one of these compositions, because I got the sense that this is not comfortable yet. Okay, let's try. Whoa, okay, let me think about this. I think I want to do the limit as x approaches 1 of 1 over the natural log of x, and then let's square that. Okay. First of all, we'll start with our innermost function, the natural log of x. We're gonna look at that as x goes to 1. What is that limit?
Would be E. 0.
Oh, not quite.
Oh,
No, you're
sorry,
thinking
0. It would
yes,
be
it's
0.
actually-
I thought
it's
the other
actually-
way around.
Yep, if it was e to the x, then it would be e. So you were thinking about the exponential, not the log. No, yes, you're right, Julia. It is 0. How do we know that?
Calculator.
Yeah, going back to this logarithm picture, like y equals natural log of x, it's good to remember this x-intercept happens at 1. Right? Also, e to the power 0 equals 1 tells us that the natural log of 1 equals 0. This is actually continuous if you just plug in 1. So you get 0. Okay, so now we want to say, let's look at the, well, now we're going to say
Yes.
equals natural log of x. And as x goes to 1, u is approaching 0. Is it approaching from the left or the right in particular? Like, is it approaching from one side or the other, or is it from both sides? That might be good to know.
Both.
Well, wouldn't it be just? Actually, no, never mind.
Yeah. So, yeah, it is both here. Yeah, if you see it coming in from this side, we're coming in from above, and from this side, we're coming in from below. Now you can see, like, positive numbers, negative numbers, right? So it is both sides. So we don't have like a one-sided limit to work with. It's genuinely a two-sided limit. That's okay. So then when we move on to our next step, make everything a little smaller. We move on to our next step with u.
So u is like y, basically. Because y is 0 at 1.
Yeah, u is like y, so temporarily, because with along each step you're looking at input output. So like usually input is x and output is y. But if you're doing a composition of functions, you say the first one is input is x, output is u.
Okay.
And then for the next one, the input is u and the output is y. Or w if you're going to have another one. If you're going to do it twice, then you might go, input u, output w, and then for the final one, it's input w, output y. The point is, you're following the variables through that chain: input x, output u, output y, like that, chaining together. So putting this in terms of u, we have u approaching 0. And then now I can write this function, but I'm going to replace the natural log of x with u. So we have 1 over u squared. So now what is the limit of that as x approaches 0 of 1 over u squared?
Wouldn't that be undefined because you can't? It'll be 0 anyways if you do like. Would you do direct substitution because it's like a constant number, or?
So we can't do direct substitution because the function is undefined. Now, direct substitution is only valid when the function is continuous, and these functions we're working with are only continuous when they're defined. So is 1/0 squared defined? It's not. So it's not continuous. So that doesn't tell us directly what the limit is. What do we know? What do we know for the limit of 1/something squared when that something is approaching 0?
Is it infinity?
Yeah, it's infinity. Again, it helps to know the graph. 1/x squared looks like this. And so here we have from both sides going up towards positive infinity here. Yeah. So here is a important point to make. I'm going to export this first of all. But you guys, on tomorrow's quiz, if the limit doesn't exist, but you could be more specific and say the limit equals infinity or the limit equals negative infinity, I want you to answer with infinity or negative infinity specifically. Okay. So this is one of the kind of annoying things about limits that technically it is also true to say that the limit doesn't exist, but it's just not as valuable as saying the limit is infinity or the limit is negative infinity. For example, why is it valuable to be able to specify infinity or negative infinity? When we were working on this problem, the first limit we studied did not exist, but it did not exist because it was approaching negative infinity specifically. And then when we carried that information through to the next step, the fact that it was negative infinity specifically helped us identify that this limit is 0, that it does in fact exist. So the overall limit did exist, but on the way there, we had to look at a limit which didn't exist, but was specifically approaching negative infinity. And that fact was helpful to us. You get what I'm saying? So I will not give full credit to an answer which is just DNE when the answer should be more specifically infinity or negative infinity. Does that make sense? Okay, now that we've established that infinity and negative infinity are like valid answers for, and valid and useful answers for limits, we should start using those whenever it is appropriate. So if you don't use that and just say the limit doesn't exist, then it's like you haven't really finished the problem. Does that make sense? So it would be, yeah, partial credit, but not full credit, basically.
So, Tristan, what you're saying is like the way you did the question with e to the 1/x. So if I do like do not exist for the x approaching 0 and then break it down from positive and negative side, will that be full credit?
Oh, yeah, as long as from the positive and the negative side separately, you are identifying infinity and negative infinity.
Okay.
So
I have a question.
It's true that, to finish answering Julia's question first, it is true that, you know, if you get infinity and negative infinity and they are disagreeing, then yeah, the limit doesn't exist. But you might want to break it down into one side and the other side. I actually should have done that on this problem. I realized that after going over it. At this problem, I just stopped when I got DNE, but actually what we should have done is broken down the left and right sides and then identified, which is why we actually did do that in the subsequent problems, but I kind of presented them as separate problems. But when we broke it down, we got infinity on one side and 0 on the other. So that the fact that we got infinity and 0, and those are distinct, like genuine, like definitely not the same thing. If that is maybe a better full explanation of why that overall limit didn't exist. It could have happened that even though we were approaching negative and positive infinity from different sides, so this limit doesn't exist, it could have happened that if we looked a step further along and just kept going, we could have got the same number here and here. And if that had happened, then this limit would exist after all. So I was actually wrong when I said, if you get DNEs somewhere along the chain, then you stop. I guess that's not actually true. You do need to look at the left and right sides individually, and follow through and see what the end result is in both cases. But that's, I think doing something like that is more advanced than I am expecting for you guys right now. So you shouldn't expect to see something like that complicated on tomorrow's quiz. Let's circle back around to Adam. You had a question, Adam.
How many questions are on the quiz?
Ish,
5.
5-ish. I
Wait,
haven't
so 5
finalized
questions?
it yet. Like I said, I haven't finalized it yet, so it's going to be 5-ish, maybe 4, maybe 6, kind of, you know, somewhere around there. Not a ton.
Okay.
Okay.
So like once we finish the tests, we can leave them, right? This is
Oh.
9:30.
No, I'd like you to stick around because it's only a half an hour and we have a 50-minute class, and I want to do I want to talk a little bit about derivatives afterwards to kind of like prepare us, you know, for segue into chapter 3. Okay. Yeah. All right. It's 8:54. We better get going. See you tomorrow. In the meantime, I do have my regular office hours and stuff. So if you did have a question I didn't answer today, you know, just let me know. Bye, everyone.